Hi, I'm Mike Russos from the .NET Customer Engagement Team, and today I'm going to talk about doing performance analysis of .NET Core apps on Linux. Now, if you've done performance analysis of .NET Core or any .NET applications in the past, you're probably familiar with the PerfView tool. PerfView is a performance analysis tool that was created by and maintained by the .NET team for gathering memory usage, GC behavior, CPU usage, profiling information about .NET applications. And it's really a very useful tool for digging into sort of finding out where bottlenecks are or just any characteristics of the performance of a .NET app. The good news is that PerfView also works with .NET Core, the same as it does with .NET Framework. So any experience you have with PerfView will transfer over to analyzing .NET Core applications. The challenge is that PerfView runs only on Windows today. So if you're trying to understand the performance of a .NET Core app running on Linux, it's not going to work directly there. Instead, we have another tool, which I'm going to show you today, called PerfCollect. PerfCollect is a script created by the .NET team for gathering performance traces and information about .NET Core apps on a Linux machine, and then those performance traces can then be analyzed either on the Linux machine using native tools, or they can be analyzed using PerfView on a Windows machine. Now, I'm going to focus in this demo on PerfCollect itself, what it is, how it works, how to use it, rather than on PerfView, because PerfView already has a lot of documentation available. If you'd like to learn more about PerfView itself, you can go out to our GitHub page at Microsoft/PerfView, and I'd encourage checking out this link where we have a multi-part video tutorial out on Channel 9 on how to use PerfView. So you can use those to learn that tool. Today we're going to look at PerfCollect, which is just sort of that missing piece that helps us get the performance information from a Linux machine. So the first thing to do is to install PerfView. So I'm going to SSH to my Ubuntu VM running in Azure. And I'm actually going to do that from two different windows because we're going to want to be able to run our .NET Core app that we want to profile in one of these panes, while at the same time running the perfCollect script on another pane. So we want to have two of these. Okay. So let's go ahead and install Perfu. I will create a directory for it. And installing Perfu itself is actually super easy because it's just a shell script, which under the covers uses other popular tools for analyzing performance on a Linux machine. So it's going to use LTTNG and perf for collecting the actual performance information. So perfCollect itself is just a wrapper shell script. So installing it is as simple as just curling down aka.ms/perfcollect. And then once we've done that, make it executable. And we do have one prereq before we run it. Since the script depends on things like perf and LTTNG, we need to run perfcollect install before we're able to use the script. So that will install the necessary dependencies. And if you're curious to learn more about what exactly perfcollect is doing, you can just navigate out to aka.ms/perfcollect and you can check it out there. You can see when we call the install command, it ends up just under the covers, just calling things like install LTTNG. So it's going to install LTTNG tools as necessary and its dependencies, depending on the Linux distro that you're using. Similarly, installs perf. So you can see it just installs these Linux tools common. So it installs zip so that it can zip all of the perf results up into an archive. But these are sort of the underlying tools that get installed when we run perfcollect install. Now that we've installed those prerequisites, we can start collecting information by running perfcollect collect. And what that does under the covers is it calls this doCollect function in the shell script. And all that's happening here is we launch LTTNG collection, And then we run perf uh, to try and collect that. You can go and look at what sorts of command arguments we pass, but it's pretty standard. It's perf record -g, and then optionally we can specify what process to record. By default, it just records everything running on the box. So under the covers, PerfCollect takes care of running these tools for us and then packaging the results up into a zip file that's easy to transfer. So now that we have PerfCollect installed and ready to go, the next thing we need to do is we need an app that we're actually going to profile. So I have something I call spin sample, and this is actually just taken directly from the Perfu tutorials. If you go out to, let's see, where is it? Here it is. Go out to our Perfu GitHub repository and go to Perfu source, Perfu support files. There's this tutorial that's used in Perfu getting started guides as an example app to profile. And it's very simple. It takes an argument which defaults to 5 if no argument is given, and it spins for that number of seconds. It spins by calling recspin, which decrements the number of seconds to spin, spins for 1 second by just having a loop that just does some work and checks to see when a second has passed. And then calls recspin helper, which is exactly the same as recspin, except that it calls recspin instead of recspin helper. So these two methods just call back and forth once a second, just looping and burning cycles in between. And the reason we have two methods instead of one is because it makes for a slightly more interesting call graph when we analyze things in PerfView at the end of the collection. So if we come back over here to my SSH session, you can see that I have that that tutorial app here. I've called it spin sample, but this is the same code that we just saw. So let's go ahead and do a .NET build, make sure that's all built and that it builds properly, and then we can go ahead and start collecting. Now, the challenge here is less about collecting the performance information, because just running PerfCollect right now would already gather performance information on the native portions of our application, on the .NET Core host, on the GC, JIT, execution engine, etc. But you likely are going to want information on the managed pieces of your application, on the .NET Core framework itself, on your code in the application libraries. And those sorts of managed code are not going to be profiled in a useful way because we won't have any symbol information mapping the perf data back to where in the code the calls were being made, since that's all managed code and it's not something that perf and LTTNG have a native understanding of. So what we need to do is we need to make sure that we're going to have perfmap files available to map from the information gathered by perf back to our C# application. So we do that in two ways. The first is we export some environment variables, perfmap enabled, com plus perfmap enabled equals 1, will instruct the .NET Core JIT to generate perfmap files for IL that it compiles at runtime. Then we also want com plus enable event log set to 1, because that's going to enable some other performance diagnostic trace emitting within the .NET Framework runtime itself. Once we've set both of those, we'll be able to get perfmap files for all of our JITted code. But a lot of the .NET managed code that you run will have been compiled ahead of time. So this will be anything that you ran CrossGen on. All of the .NET Core framework is compiled ahead of time. And it's actually possible to use our pre-compilation tool CrossGen to generate perfmap files for these native images. But we need to have CrossGen in order to do that. Fortunately, PerfCollect makes this very easy, because PerfCollect will call CrossGen on our behalf and generate all the necessary perfmap files, but we still need to have the CrossGen tool available. The easiest way to get it is just to publish our application, because when we publish it, we'll have to restore the Microsoft NetCore App 2.0 NuGet package to include in the self-contained publish output of our application. And when we do that, CrossGen happens to be one of the tools that's included in that NuGet package. So I'm going to publish my application standalone for the x64 Linux runtime. And as part of doing this, as part of this publish process, since we're not publishing in a framework dependent way, we're publishing a self-contained app, we need to have all of the framework dependencies, the .NET Core, the .NET Framework, all locally so that we can distribute them with our app. Since we've done that, we now have, if we go look at our NuGet packages, we should have a runtime.linux x64.microsoft.NET Core app 2.0 package, and inside there, there's a tools directory which contains CrossGen. So now what needs to happen is by convention, PerfCollect will look for CrossGen next to libcoreclr.so. So we just need to copy this file next to our libcoreclr.so. Now that might be in a couple different locations. It might be if we're going to run our application using the .NET CLI, then we're going to use the shared .NET Core installation on the machine. So the libcoreclr.so file would be under user share .NET shared. I'll just type it out so you can see it. It's under user share .NET shared Microsoft Net Core app 2.0. So we'd want to copy CrossGen there. On the other hand, if we're going to use our self-contained published output that we just created by publishing our application, then we'll have a libcoreclr.so local to that publish output, which is going to be used. So in that case, we would need to copy this next to bin debug netcore app 2.0 Linux x64 publish. Okay, so now that's done. And we can actually go take a look at what's there so you can see that that was the right location. Bin debug. And if I search for libcore, you'll see that is where libcoreclr.so is, so that was the right place to put CrossGen. Now that CrossGen's in place, PerfCollect's going to be able to generate our perfmap files for native images, and we have our environment variable set to be able to get perfmap files for JITted managed code. So now we're ready to actually run the PerfCollect script and gather information on our application. So in order to do that, we're going to hop into that PerfCollect folder, sudo perfcollect collect, and we have to give a name to the trace that we're going to save. We'll call it sample trace. Over in the other pane, we're going to run our application. We may as well use our published output that we created. So I'm going to run spin sample over here. So run perfcollect. Once perfcollection started, I start my application, which spins for 5 seconds. Once it's done, Control C, breaks. We process this, we generate native image files, save native symbols, export everything, and now it's packaged up into this sample trace.trace.zip file. If you're curious, we can actually unzip sample trace.trace.zip to see what's there. And you'll see it puts it all in this folder. And so in here we have the perf data that was collected. We have the perf maps that were generated by the JIT. We also have the native image perf maps that were generated by CrossGen. And in fact, these are just normal perf files. So if you're comfortable doing performance analysis on a Linux machine, you can very easily do that here if you'd like. You can just run perf report, and you're going to get the information you would expect to see when using perf. And so you can see, okay, here we have exclusive and inclusive time spent in these different processes. So we can, sort of look at that as you normally would. You come down and say, okay, here's this recspin function, which was 27% inclusively of all of our time. It didn't actually spend much time itself, but if we dig in, we see, oh, it was called from recspin helper. We can sort of go back up. We can see a spin for a second is where we were actually spending some time, see what called it, and so on. You can use this the same way you would do any Linux performance analysis. We actually also have some scripts in PerfCollect that will allow you to do this without even unzipping the archive. If you do perfcollect report, or PerfCollect view, sorry, that will give you the same sort of perf analysis directly from the zip file. So that's an option as well. Now, for a lot of .NET developers, they're going to be already familiar with PerfView and would probably like to continue using that tool. So if you want to do that, that's something that PerfCollect is made for. It gives you this zip file. All you need to do is copy that zip file onto your Windows machine and launch PerfView like normal. So let's go ahead and copy that file locally. We're going to copy it from micro at microunix.cloudapp.net. We're going to copy micro perfcollect sample trace.trace.zip, and we'll just put this in the current directory. It should be copying. Come on. Not sure why this is being slow. This should be pretty fast. It's not all that large of a file. Okay. Connection closed. Did I type something wrong? Let's give it another shot. Okay, there we go. This looks more like it. Okay. So we now have that file locally. So what we can do now is back on my Windows machine, just from the Linux subsystem shell here, I'm launching perfview, and I'm providing sample trace.trace.zip as the file that we want to analyze. So we launch that, perfview starts up. Now again, if you aren't familiar with perfview, you just click on this tutorial link when you start it up, and it's going to walk you through sort of profiling and understanding all of the reports for a sample application. Makes it easy to use. In our case though, we can just hop in here to the CPU stacks. You can see we've got all of this. Right now it's grouped by module. Maybe I want to see it more granularly, so I'll remove the grouping. But we can start to understand what's happening within our application. If we sort of look in here. For example, we see a lot of time is being spent in this native read MSR safe function. Well, why are we there? Well, we can come in here and we can start to drill out looking at callers until we discover, hey, there's something called spin for a second, which is called from recspin and recspin helper, and that's calling this thing where we're spending 20% of our time. And that's just 20% of the profile time. This isn't even specific to this particular process yet. We're going to find out it's the vast majority of this process. And so we can say, okay, well, we need to go check that out. You also could come at it sort of from the other direction. If you wanted to do more of a top-down approach, you could sort by where you're spending your time inclusively. We see that here we have spin sample main. Come in here, we can go look at our callies, and we can see, all right, spin sample main's taking most of our time, but where within spin sample main are things actually happening? So we can jump in here, let's see, sort of dig down till we find something interesting. Here we go. Here's our managed main method, and we see, oh yeah, most of the time in that main method, maybe we'll even just drill into this in a separate window that focuses specifically on it. And yeah, we can see 99.8% of the time that our application is running, it's in recspin. Oh, that's interesting. Come in here, 80% of that's in recspin helper, 20% is in this spin for a second. Recspin helper, though, also goes into spin for a second, and all of a sudden we start to get a picture of how our application is spending its time. Again, I don't intend for this to be a deep look at PerfView. There's already a lot of very good learning materials available for PerfView, but I wanted to just demonstrate how you can use the PerfView tool even when you're interested in understanding performance of a .NET Core application running on Linux. And you can do that using this PerfCollect script to gather that information that then you can go ahead and analyze either on your Linux box or back on Windows using PerfView. Hope this has been helpful. Thanks.